Hello, my name is John Mount. I'm a principal consultant at a data science company called WinVector LLC. What I'd like to do now is run through mastering the process of forecasting the future using time series. The outline for this talk is I'll go over who I am, the motivation for even using time series or wanting to forecast the future, a couple very small real-world examples, an outline of the methodologies used in this field, and an artificial problem that we've designed to have the sort of problems real-world users run into right after they leave the academic presentations. Things like not having to predict below zero, things that are commonly ignored in academic teaching of time series, but the sort of pathologies you run into with real data instantly. I'd also like to call out something I call the liar's graph, which is this accidental graph that makes bad predictions look really good, which you need to try to learn how to avoid and teach others to avoid. Then I'm going to get on my hobby horse and solve everything using an open source Bayesian reasoning package called STAN, which I really like. So who am I? I'm a general partner at WinVector LLC. We do data science training, consulting, coaching, evaluation, and development. I'm one of the authors of Practical Data Science with R, and we also do a lot of work in Python with several PyPy packages publicly motivated. But let's go back to time series and try to motivate it. For some businesses, there's great value in being able to estimate the future. And the value of that depends on what your business does and whether you can do things to change the possible future, or whether planning or pre-allocation of resources or pre-accounting of quarterly revenue matters to you. I am sharing the ideas in this talk and all of the code in Python and R in the supporting materials link, even though we're calling this a workshop. But you should be able to rerun almost all the examples here mechanically by going to the shared public GitHub repository, which I'll share several times in this talk, including the slides. So here's a real world data example. This was from a fun article from Stack Overflow some years ago, around late 2017. And it was showing that the trends of Stack Overflow question tags, so the formation of questions on Stack Overflow, had this dramatic upward trend for Python. So they've seen the data up through late 2017, and then they applied a standard time series extrapolation to say that Python had not only started to cross some of the more popular languages such as JavaScript and Java, but that difference would continue to widen. Now, was that a good prediction? The answer is yes, that when we moved forward the 2-year interval that they forecast into around almost late 2019, the observed counts were very close to the projected line and within the error bars they drew. That's a good prediction. Now, they used some time series software. They chose a seasonal low-S STL methodology, which is quite good. But is that really better than doing it by hand, say by laying a ruler on the data, as I illustrate here? And the answer is it is better, because you can do this for many data sets. You can claim some degree of objectivity. You don't get caught with your hand directly on the ruler pointing it up or down. And you have concepts other than straight up as possible. Now, is this prediction reliable into the far future? And the answer is no. This is the Python question formation rate at Stack Overflow, extrapolated from further out. I've just zoomed into 2015. And the shaded area is the training data, the x-axis is year, and the non-shaded area is the future. And we're past 2019, 2020, so we know more of the future. And what we can see is when ChatGPT was introduced, it knocked the trend off its upward trajectory and into this more BAS-like product lifetime thing. So at least as far as questions forming on Stack Overflow, the percentage of questions, which is already normalizing for the size of Stack Overflow, on Python is starting to collapse. And that's interesting. Now, this was outside of their projection range, so this is not their fault. They didn't miss this. And how would they have known from just the graph of Python usage that something like ChatGPT is coming and what month it would be released? So some demotivation. This is a quote from the researchers at Facebook that produced Profit, and I agree with it. that the time series literature is sufficiently complicated and specialist that even a pretty good analyst can incorrectly set a lot of the parameters, which can have some bad consequences, or unknowingly bias the predictions to represent the mistake made in fitting versus what's actually likely to come in the future. In my opinion, time series material is overly technical, undertaught, and often misexplained from a tools point of view instead of a tasks point of view. And I'm going to try to not sink so deep into that in this talk, though this talk is a workshop on this fairly technical topic. Time series forecasting is pretty technical compared to usual predictive analytics statistics. So here's an example of an experience, and I don't want to call out who, but it's a very bad typical experience of dealing with something like an ARIMA reference. So ARIMA is one of the acronyms for time series, Autoregressive Integrated Moving Average Time Series. And the panel on the left is just an excerpt of the multi-page diagnostic panel that the analyst is supposed to produce and understand before they do the time series projection. Now, this is bringing in a bunch of technical issues they didn't care about going in, or certainly they were not business issues. Then, after passing all those tests, like it checked for normalcy, it checked for certain anomalies, it checked for unit roots, all non-business but ARIMA concepts, we go to project out in time, where we have this graph where the x-axis is time, the y-axis is the quantity we're trying to project, the curve is the history, and the blue is the projection into the future. And this is a degenerate projection. It's basically saying the entire future is a single constant, that's that horizontal line, and there's great uncertainty as to where that is. That's those hugely widening opening curves. And in particular, in no point in the past was the curve flat. Sometimes it went up, sometimes it went down. We may not be able to project which, but flat is not one of the projections. It's basically the fitter failed quietly. And this is in their training manual and not called out as a fit. Just as called out as all, this is how you work, here's your projection. Whereas this is a disaster. I've actually gotten a little cranky about this and probably written a couple articles, too many, on this sort of thing. But here's some more examples. Like the bottom left graph is an artificial example that looks a lot like sine x. The orange dots are the time series going forward. And then the green curve is an extrapolation using one of the standard methods. And again, you see it just degenerates. Doesn't start flat, but goes flat. Similarly, this furry graph in the middle is a failure, and this other graph on the right is a failure. And this is trying to predict something as simple as tides. And it's picking really bad ARIMA parameters. The 10, 1, 0 in the middle diagram, those are the controls for the ARIMA. And that's a ridiculous set of parameters. I don't want to get into them, but that basically be suspicious of any auto ARIMA, auto ML kind of things where it goes, I'll pick the important parameters for you. If that was such easy law, that would be in the package. Well, these are in the package, but it turns out it's picking parameters. They're very bad in addition to doing a bad job. Now, back to business applications. Tides is a solved problem, even though the previous slide failed on it. This is Lord Kelvin's machine from 1876, where he literally set the dials, turn the crank, and a little needle draws the projected tides for any given location onto a spool of paper. Super accurate. But for what's the point of predicting the tides? Well, it can help you schedule your ships. You don't sail against the tide. So predicting a future you cannot change can be useful. Predicting a future you can change, such as sales, where you can do more marketing and more outreach to try to pull them off sales you don't want, or even mispredicting the future can be useful. As in all cases, the time series prediction is what is the typical expectation, not what's actually going to happen. And knowing when you started to deviate from the expectation could be signs that you're in an anomalous situation and need to interact. So sometimes in many businesses, you tune the business activity to match the projection. So let's get super technical now. Let's go over the broad families of time series methodologies. And to work through these, or how the analyst adds values, you don't just try every single methodology. You're going to have to try several because data science is unfortunately an empirical science, which means you can't always do everything from first principles. You have to try. However, you want a problem specification that represents the physics or mathematics of the business you're trying to model. For instance, if you're a restaurant by word of mouth, you believe your customers are autocatalytic, that a happy customer may bring in more happy customers later. That can be reflected in certain models. If you're a parking lot that you don't do marketing, maybe your biggest thing is external influences such as seasonality or external events. So maybe there's a different model you would use for that. You also must be able to extract structural advice from the model. Like, is this a stable business? Is this an unstable business? And that, I think, sort of argues somewhat against black box models. For a black box model, you sort of have a model where you maybe have the predictions, maybe they're right, maybe they're wrong, but you have a lot less explainability is the nature of the phrase black box. Some of the dirty secrets of forecasting is always extrapolation. And that's always deadly. That most machine learning triumphs, even AI, deal with interpolation. That if the problem is inside the cloud of other problems, maybe we can just write down a solution in the cloud. So going out is always bad or dangerous. Things change over time. Time series predictions or forecasting have a built-in concept drift. The model is necessarily trained in the past and then used in the future to predict an even further out future. It used to be hard to convince people that concept drift is so important. Then COVID happened, and it's hard to convince people that any sort of forecasting is possible at all, which it is. It does remain possible. You usually have an extremely small amount of training data, especially if you start thinking about things like dependence and independence. The problem is, like, if you have a parking lot with 100 cars arriving in an hour, that's just one number, 100. You don't often treat those as individual events. And subdividing your data into finer and finer time buckets, like cars per minute or red cars versus black cars, that doesn't actually give you more data. It just gives you more opportunities to overfit because they're all correlated and noisy. So really, there's a natural amount of data for a given time series problem. And for like a monthly prediction where you have 3 years of training data, that's only about 36 observations. So it's very small. So you really have to be statistically rigorous. Many of the models can imitate each other. They can make identical predictions with different parameters. This kills the usual methodology of we will just use quality of training fit to find the best model. Yes, you'll find the best model, but you don't know that you've eliminated other models that may have been similarly good and have different predictions. And usually, I feel you want to actually forecast unobserved quantities. If you're a restaurant, you really want to know demand, not how many people sat in the restaurant every evening. Because if you were full and turned a few away, you have a censored observation of demand. So you want this sort of uncapped or hidden variables, which is ideal demand, not how many people are in seats. And this, you're predicting unobservables, is interesting. In my mind, the major methodology families are the exponential smoothing models, which say things evolve in a way that we always know. ARIMA models, which say things evolve sort of an autocatalytic way, increases beget increases, volume begets volume. Brute force modeling methods, just reducing it to a predictive analytics task, which actually works. And decompositional or attribution or hidden state methods, which are what I'm going to emphasize in this talk. Back to our opinion on black box models. Your ideal analyst or data scientist understands your business, or at least sympathizes or empathizes with it, and understands the modeling methods. So when they get a prediction, they know whether it's a consequence of your business, whether it's important to your business, or whether it's a consequence of the model and not of reality. A domain expert might be able to make good predictions without knowing a lot of math. They know the business. A modeling expert might be able to provide good predictions, good advice without knowing a lot about the domain, because the succinct math may carry them. An auto ML style methodology, or a black box, or just put it to an AI, that at best gives you reliable predictions and not always. And it basically lets somebody that doesn't care about your business and doesn't care about the structure of time to do the work, which is not favorable. Now, back to our outline of modeling methods. The first set are essentially exponential smoothing models. So these say basically, it's a noisy world. Everything evolves the same. If X is our vector of observations, then a smoothing curve is the first smoothed curve, S0 is X0, and each one in the future is a little bit times the current measurement plus a little bit times the past smoothed thing. This is called an exponential smoothing window. And the idea is that there's some ideal process that you're just observing with noise, and you just want to extrapolate out. And this can do an average or a trend or a changing trend. The methodologies are called Holt-Winters, common filters, and the only parameters are the learning rates. Just how fast does the system evolve to take the current measurement to replace its previous averages? These are good, especially for short-term predictions. The next set of methodologies, which is related to this set and the previous set of methodology related to how that Stack Overflow prediction were done, are the RIMA methods. These are the so-called autoregressive, that there's some sort of variable, call it y, that we're measuring, and it's related to the current value is related to the value 1 time tick ago and 2 time ticks ago. For instance, the expected value of y might be 1.975 times y previous minus y previous minus 2. And this is sort of a trick. This will basically draw a sine x of a given period. And then you can iterate this forward. So this RIMA system can do a lot more than just linear or exponential trends. It can do sine x, cosine x. You can add things like seasonality, which gets you from a RIMA to SARIMA. You can add external regressors, which I think is super important and underrepresented, and that takes you from a RIMA to a RIMA X, RMX, X for external regressors. And I have worked out some examples of this in the given links. The next set of methods are brute force methods. And I actually rather like these, and some of these are used by the neural net and deep learning community. But you just say, if y is the quantity we're trying to predict, and if so then y at time t plus k, t being now, k being k ticks out, our estimate of it could just be a function of a few y's. So we're basically not treating time as a special variable anymore. And in particular, in the ARIMA, a 2 time tick out prediction is a 1 time tick out prediction applied twice. In this case, a k time out prediction is just a direct function. So we fit one function to fit 1 tick out, another one to fit 2 ticks out, and another one to fit 3 ticks out. This gives us a sort of album of models, which really hurts explainability, but it's actually a very effective method, and a lot of the neural net systems do use this sort of thing as they convert the time series problem to a series of basically predictive analytics machine learning problems. Now we're back to my favorite methodologies. Profit is one of them, and it's decomposition or attribution. Now, profit is hardwired for business clock. It essentially, its time unit is a day. It needs a time index that is real days, like January 15th, 2020. You tell it when, and then it can join in certain things like seasonality and give you predictions. And what it also gives you, in addition to predictions, is the graph I show here, is the decomposition of the model into a trend component, a seasonal component, seasonal in this case being both day of week and month of year. So there's 2 seasonal components here. And then also an external regressor component, which is the last part of the panel. So profit decomposes your past data, which is just a count per day, into 4 observations per day. What fraction of that count was due to trend? What fraction of that count was due to day of week seasonality? What fraction of that count was due to yearly seasonality? And what fraction of that count was due to external regressors? These external regressors could be basically like issuing a Groupon coupon back when you used to do that. So you could say, what fraction do we estimate came from that coupon if it weren't labeled? If it's labeled, that's even better. But if it's not labeled, this is the sort of decomposition you want. Then it uses this decomposition to project into the future. The theory being, you can project each one of these curves into the future. Trend just goes up. That's trend. Seasonality, you know when the next tick is by the curve repeats. It's cyclical. And then for external regressors, you need to know those values in the future. So you don't want to fit on something like weather that you can't predict, but you might fit on something like external events near your restaurant, which you can buy from various data providers. Prophet has the right ideas. The user is allowed to specify the structure of the problem, which is not true for ARIMA. With ARIMA, you are taking the structure of the problem from the package author. So you can say seasonality is multiplicative, that there's 10% more cars in December than November, or seasonality is additive, that there's 10 more cars per day. And, depending on the nature of your business, you might have different opinions as to whether these adjustments should be multiplicative or additive. Prophet is specialized and ready to go. If you're seeing as dates, it has all the optimizations for dates already ready to go. And it uses this Bayesian inference system called STAN, which is where we're going with the talk, as its underlying engine. My opinion is good time series solutions combine a few ideas from all of these methodologies. And most of these methodologies get excessively technical and restrictive if you go down into them too deep. And that's kind of why I like the STAN, is it can imitate all the others. It's the implementation of one of the most flexible ones, Prophet, and it's a very sensible way of going. So let's move on to our example problem so I can try to justify my opinions. So I, as a business serving consultant, I'm very interested in non-negativity, that if I'm modeling a restaurant, I can't predict -5 customers. Yes, I know I can round that up to 0, but I'd like the model to respect that. And I also need external regressors. Now, which is things like, if you tell me the parking lot next to my restaurant is closing next week, maybe fewer people come to my restaurant. Or if I'm a parking lot and you tell me the restaurant's open, maybe more people come. So I need external regressors, or at least every business really wants those. And Arimax, Sarimax, and others don't let you specify how the external regressors enter the system. For each external regressor, one can think, at least, is it durable? Meaning, does it deliver customers to my restaurant that come back? And like marketing or reviews might deliver durable customers. Or is it a transient external regressor, such as a movie right next to me? Yes, those customers come, but most of them don't come again. So if there's another movie, I get in more, but I have these transient ones. Most ARIMA systems only deal with transient external regressors, which Hinman calls regression with ARIMA residuals. There are some that deal with durable, but I haven't seen any that allow you to do both or control, and business needs that. So let's go to our notional artificial non-real world example. We're modeling a restaurant. Our time tick is days. We want to predict how many customers come every day. I've made this super artificial and autocatalytic that customers beget more customers. I'm not doing day of week effects or seasonality because those are quite easy to do, so they don't show the difficulties. And we're going to model our restaurant population as 2 subpopulations of guests, loyal and transient. And I'm going to do that in equations because, as ugly as equations are, they're slightly more verbally compact than words, though I will read these equations out to you. And these are the only equations we're really going to use. Everything else is just an edit of these 3 lines. So we're saying that for a given date, there's a number of loyal guests. And we're going to model that, right or wrong, as a linear function. There's an expected number of loyal guests, that's beta loyal. There's a number of loyal guests as a function of the loyal guests yesterday. That's our first autoregressive factor. And there's it's also some function of the loyal guests 2 days ago. So this is an ARIMA-like equation. It says that the quantity of something depends on observations of that same something 1 or 2 days ago, hence the word auto. And then there's this external regressor in the loyal guests equation. Beta review times the intensity of a review given yesterday. So we will fit that from data. Now, we also have transient guests. So transient guests is the second line, and it says the transient guests all come due to external stimuli. And we've only written down one external stimuli. What's the size of the event near our restaurant that day? And some of them come eat. And so our modeling task is to get that conversion from event sizes into restaurant guest sizes, so we would infer the beta events. Now, final and last line of the equations, total guests is just loyal guests plus transient guests plus some more noise. The point is, only total guests is observable. All the other numbers, transient guests and loyal guests, are not observed, and all these coefficients, these betas, are to be inferred. We don't know them going in. It's the model fitting task to find these betas. And since loyal guests and transient guests are not observable, we also have to guess at those values as part of the model fitting. And that's kind of my heterodox point in this talk, that inferring this decomposition of your past system, which something Prophet does for you, is actually possibly more invaluable than even forecasting. You can make policy choices for your restaurant if you even just know the ratio of loyal guests to transient guests. So the equations in detail are written down. It's essentially just saying what I said. And now we get this question again and again. What good are external regressors if you need their values in the future? Well, the point is that people are willing to sell you the values in the future. For instance, PredictHQ gives you lists of predicted events with magnitudes, with lat longs. So there's things you can do. Okay, so is forecasting really everything? No, as I said, even knowing the decomposition of the one observable variable per date, total guests, into two more variables, transient guests and loyal guests, and also pulling off the noise, so actually it's three variables, is super valuable. That tells you the nature of your business. Can standard packages solve this? Again, this is the exact same set of equations. I'm just putting them there for memory. Yeah, if beta review is 0, forced to 0, this is regression with ARIMA residuals. If beta events is 0, this is a different sort of RMAX. Some econometricians use this to study policy. I think there's one Python package that does it this way. It's really hard to tell from some of the packages, unless they write down the recurrence equations, which one they're doing. And also notice for ARIMA, I've not really talked about any of the classic ARIMA parameters like P, I, and Q. Okay, so back to our artificial example. The x-axis is our abstract time tick. Think of it as days. The y-axis is the count we're trying to predict. There's an unobserved process generating this of the y autocorrelated or autoregressive, or the loyal customers. We have both durable and transient external regressors. Transient external regressor might be a movie near your restaurant, and a durable external regressor might be a positive review of your restaurant. So this is a completely artificial example, but it's real world in the sense that it's not what's taught in the books, that you have all these issues that you'll get when working with a business, that the noise model's not really correct. It's not really normally distributed. We're not modeling a reservoir. The counts are non-negative, so they're truncated below. The counts possibly are bounded above by the capacity of a restaurant. And there's sections where the future is not a function of the near past. For instance, when the model hits 0, it eventually comes out of it. But if the last few observations is 0, it's very hard for the model for an ARIMA model to make an interesting prediction. And the thing that we didn't really put in, which saves us a lot, is we'd put in no strong seasonality, which saves a lot of businesses, and we should definitely model it. But I wanted to talk about the problems without making this too complicated. So here's a zoom in on our training data. In this right region from around time tick 970 is where the system is 0 for a while, and then it comes out of it. And then here's our held out test data. And so it comes out of that 0 region, arcs up and down, and we're saying we don't want to predict one time tick out. We want to predict the 20 time ticks out from time 959 to get all these other time ticks. This is our near future arc. That's the business request, is predict 20 days out from now. So what I'm talking about when you say predict 20 days out is trying to avoid this horrible artifact I call the liar's graph. And we saw this a lot. I saw this a lot when I was in finance, that someone would say, well, what's the way we usually measure model quality? We put the prediction on the x-axis, which is key, and we put the actual on the y-axis, and we do a scatter plot, compute some summary like root mean square error, RMSE, or R squared. We want RMSE to be small. We want R squared to be near 1. And here, this is a great R squared, 0.78. That's fairly large. This is a good prediction. This is a lie. The lie is I'm just saying that the next time tick will be the previous time tick. So I'm just lag by 1. So I'm never predicting 20 days out. I'm just predicting 1 day out, and I'm repeating that 20 days into the future. So what you really need to do is insist on an out of sample prediction graph. So this entire graph is out of the training region. The liar's prediction using the previous time tick is now forced to use the previous known time tick. So at time 990, it can't use time 989 as its prediction. It has to go all the way back to time 959 because that's the last time it knew. So that prediction is going to be just a constant, the green line. That green line is not a good prediction of that future. So this graph is always using the previous time tick, even though it's not known. This is using the most recent known time tick, which is always time 959. So be very careful in that evaluation. Always insist on a time-oriented out-of-sample graph. Okay, so let's just do some results. So here at GitHub, I share how to solve this using standard or Emacs, using the stats models package. And it does an excellent job. And this is why I consider the problem easy, that Emacs nails it, which Emacs is pretty powerful. So we get this incredible R squared of 0.96, which is sort of how you know this is an artificial example. It gets the fact that the external regressors pull the graph up and down, in addition to any trend-like thing. So this is, quote, an easy problem, unless we're careless. So this is a AI package service called TimeGPT. So it had the disadvantage we had to send the data to it and get it back. We trained it at a much larger interval than shown here. We're just zooming in. So the line is the historic data most close to that region. We're going to go to the future. The green region, the line and ribbon are TimeGPT's predictions and 95% confidence interval. And the circles are the future that eventually arrived, the same test data we've been talking about. And you see it's a pretty bad prediction. That it's a line, at least it has a trend, so it's probably somewhat of a degenerate fit, and it's not great. But it's sort of, just because it's using more sophisticated methods doesn't mean it's a better result, because in time series we have so little data, you really have to be very strict in your methodology choice. Here's the Stan result, and this is why we love Stan. It's about the same quality as the REMA. It seems to maybe not quite like the external regressor as much, but it shoots its line right through where the future data later arrives, and it does have a good R squared. This is not the liar's graph, that each one of these predictions is using no data past time 959. And this is the extra thing that I kept advertising, the decomposition, which Prophet already had, and Stan also can produce if wired up right. So the training data is just the top left panel of this graph, just the dots. The training data is then in the shaded regions, the training region. The system then decomposes that into the autoregressive system. So that's the part of the system where customers are recruiting other customers. So that's the middle panel. And to the transient impacts, like when told there was an event near it, did that add or subtract customers? Like, for instance, a road closure near it can subtract customers. And not shown is the noise, that the first two curves don't quite add up to the first, because there's also a noise term, which not portrayed just for legibility. And what we can do is we can extrapolate the autoregressive system into the future. So the middle, we estimated the thing on the left, did not observe it, we estimated it, and we can push our estimate into the future, and its little error bars open up. And we can also push the transient effects into the future, because we're assuming we can join in a database that tells us when these future events are, and then our model's just assigning magnitudes, up or down. So we can project these two panels into the future, and then our prediction is then the sum of the panels, which is then the top right. So the training data is only the top left panel. The forecast is only the top right panel. A good modeling system such as Prophet or Stan gives you 4 more panels. past unobserved state, past external impacts, future unobserved state, future anticipated external impacts. And we get coefficient estimates. The dotted lines are the actual betas or coefficients that were used to generate the artificial data for the transient and durable impacts. And the shaded curves are the estimated distribution from the STAN model. And it clearly did better on the top one than the bottom one. We can't really say if it's biased without maybe running more models. It certainly underestimated the orange, but we don't call that a bias unless it's systematic and it would do it with more and more data. So how we solved? It's really engineering simple. We take the set of equations that we've had from graph to graph, which I've now put here small, and we take our data and we stuff them both into the machine called STAN, and then we literally turn the crank. Let STAN simulate and resimulate results. And I've shared my entire solution here at this link. So since I've come out against magic, I need to demystify or demagic STAN. So STAN is what's called a Markov chain Monte Carlo sampler. What it does is it generates solutions that are compatible with the constraints. The equations we give are the constraints. And it biases the sample to solutions that are more and more compatible with the constraints. And it does it in a way that would be quite difficult for you and I to re-implement. That it generates solutions that are 1 in a billion appropriate or 1 in a trillion appropriate. So it really ignores the bad solutions. And that's the magic of STAN. And, a STAN simulation can take 5-10 minutes, which is much faster than training a neural net, but much slower than any of our linear models. STAN is a Bayesian inferer. So it makes probabilistic statements that it says this is a likely solution, this is an unlikely solution. And it returns distributional answers. As we saw, we can have these error bars and stuff. And it really subsumes a lot of ideas like particle filters and importance sampling. So if you're worried about sexy trade names, many of these other systems can be implemented in STAN. And unfortunately, it's a fairly high dependency system. It requires a C++ compiler and linker. It captures your equations, writes out C code or C++ code to run fast. So it's a little tricky to install, but it's not too bad. So what we did is we asked STAN to use a hidden state method to solve an Armax style model. So those equations are Armax style. And we said, instead of using the Armax solver, which itself is quite sophisticated because it's reasoning over hidden state, we said, STAN, guess it yourself. And it did. Now, that we paid for that as an inefficiency that took STAN 5 minutes instead of Armax 500 milliseconds. But we can afford that. We directly, again, we specified there's 2 unobserved subpopulations, and we're only observing the sum of those 2 populations. So we're asking STAN to unstir a mixture. And it somewhat can do it because stability of counts is probably due to the autoregressive subpopulation, and unstable counts are probably due to the transient population. So there are clues when you have 100 customers in your restaurant one day and 50 the next day, whether you're largely an autoregressive system or largely a transient system. And that ratio is everything. And we don't need any heuristics to get that ratio because they're all baked into STAN. Why it all works is Bayes' law, which is just saying that if the data looks plausible with respect to your guessed parameters, then your guessed parameters are somewhat plausible with respect to the data. So I'll say that again. If the data looks like a plausible outcome of your parameters, then your parameters are possibly a plausible outcome, a plausible match to your data. And you'd think that reasoning chain is so weak, and they differ by priors. That's why Bayes' law has 4 terms in it and not 2. But you say that reasoning chain is so weak, it'd be computationally expensive to reverse that. And it is, but that's what STAN's doing for you. This is the STAN solution in detail. You just write down what you want in code. The first block of code is saying that the autoregressive visitors, y auto, is normally distributed as a function of b auto 0, that intercept, plus some function of the people that visited a day ago and some function of people that visited 2 days ago. The colon notation is us doing range slices on these arrays to get that. So we can do vectorized work in STAN, or we can criticize the observations as we do in the for loop, where we're doing the usual Tobit style trick that if an observation is positive, we assume it's normally distributed. And if an observation is 0, we assume it could have been -1, -2, -3, and we sum up across all those probabilities. The difference being whether we call normal LPDF or normal CDF. So summing over all possible negative possibilities is built into Stan quite nicely. What we get back from Stan, and again, that methodology is a Tobit trick. What we get back from Stan is this data frame. Each row is a different sampling history of Stan, so a different possible future. That's how Stan manages its uncertainty. And the columns are the things we're measuring. So for every column of our system, we get Stan's estimate of that 4,000 times. The thesis we're trying to support with all this work is ability to specify actionable structure beats power in forecasting. So someone's super magic algorithm, if you can't specify what structure it's working over, is going to have less utility to you than one where you can specify the structure. And part of that is because we have so little data, we cannot use quality of fit to be the only determinant of structure. We have to put useful modeling bias in. And the other part of that is often we want more than the forecast. We want to know things like what fraction of the customers in my restaurant are transient versus loyal. And so we don't want to lose that control. So follow-up resources. Everything in this talk, the slides, R worksheets, Jupyter Python notebooks, showing how to do this, showing how to use Stan, showing how to use stat models, showing how to use the fables and forecast packages are here. Some of the perils of time series forecasting, an article I wrote, a defense of the brute force methodology of just trying to reduce the problem to a predictive modeling problem. After when all this talk I said of hidden state, you'd think that just doing brute force is a sin. It's kind of not, because when you do that time index that I'm not going to iterate the prediction, you get rid of a ton of the REMA problems. Like you don't need to worry about unit roots because you're not iterating. And then, thank you for your time. And here are the follow-up resources that we're sharing. Again, everything is here, including these slides.